Welcome to Stat 310 Lecture 3. So hopefully you've watched the first two lectures, and so we're moving on to Lecture 3. So we're going to continue on with our review of 309 material that's going to be relevant to this course 310. And in particular today we're going to focus on convergence of random variables. So this is again something that you've seen in Stat 309 or Math 431 or whatever prerequisite course you took. So we're going to first cover that and then discuss some related concepts to the law of the law of large numbers and then the central limit theorem, which are both related to convergence of random variables. And this is going to be a very important topic in this course as well, because we're often going to see samples where the sample size is large, and so the notion of convergence plays kind of a really important role. So if you're thinking about looking at samples of like hundreds or thousands of people, similar to what we saw in the voting example, the notion of convergence is really important, and that's why we're going to cover that in today and possibly into the next lecture. And I'd just like to begin with a few generalist announcements. So the first homework is due Thursday, September 10th. So hopefully you're aware of that. At this point, I may have made a mistake earlier and said it was September 11th, but it's actually September 10th. Every homework's due Thursday of each week. So just make sure you're clear on that, and sorry about that confusion. The other thing I'd like to point out is, so you've already had two lectures, so you've potentially got to see what that's like, and it is, I can imagine, potentially a little bit dry to just sit there and watch lectures at home, and it doesn't feel very engaging. So I just want to remind you guys to take advantage of office hours and to email me if needed. So the office hours are every Thursday right now. If for whatever reason you can't make those office hours, please feel free to contact me. I know that it's difficult when there's very, very little face-to-face time with the lecturer. So I'm going to try to make myself as available as possible by email, and then also maybe through the Canvas website we can set up some discussion forums. But I want to make sure that when it comes to interaction with me as a professor, you need to you need to take some initiative in emailing me, and I'll and in turn I'll be as responsive as I can. But I encourage you right now to kind of take advantage of office hours. So if you're going through your lectures and writing down questions, please feel free to make an appointment and come to office hours, or if you can't do that for whatever reason, just send me an email and we can set up an appointment. Okay, so now moving on to the material today. So again, this is something that you've hopefully seen before, but potentially it's in the back of your mind because it's been a while since you've looked at probability or 309 material. So the general setup, and we're getting into this notion of convergence. So we want to change our mindset a little bit to start thinking about sequences of random variables. So here we're thinking about a sequence of random variables, y1, y2, y3 up to yn, where n gets large. So n might be like the sample size of 100 or 1,000. To take a concrete example, and one that we've already seen a lot throughout, and we're going to see a lot, especially in the next few weeks, is the sample mean. So if you look at x1 through to xn are independent random variables, like the voting outcome for different people in a sample. X bar n is just is essentially the sample average of that. So 1 over n times the sum of the xi's. Okay, and so we can think about sequences of random variables in this context, because if we let yi equal to the mean of x bar I, as I increases, or as the sample size increases, we notice that random variable, which we're gonna in this course later call a statistic or an estimator, that is actually going to change. So you can imagine that if you have a sample size of 5, you're going to get some value for the sample mean. You're going to get a different value if you go up to, say, a sample size of 10 or 100. And so this is a kind of a changing a random variable that changes with n. And so the question we'd like to ask is, does yn converge to some random variable y? And that's where we're going to introduce this notion of convergence of random variables, which you've hopefully seen before, but we're going to revise that. And there'll be questions on the second homework related to this as well. So let's return to an example that we finished with in the previous lecture, and one that's going to come up a lot in the next few weeks, and so one that you'll hopefully be really, really comfortable with. And this is a really good example to focus on as well, because it's one where we can hopefully see these concepts, a lot of concepts that we can encounter in the course. Can really be related back to this example, and it's also one of the, I think, the more natural examples to understand. So here we've got n independent random variables, or any number of independent random variables, because we're going to talk about n potentially varying here. So once again, we have independent random variables, and we're going to let x bar here be, and I'll use, to be consistent in this lecture, I'm going to use this notation x bar n throughout. So x bar and x bar n mean the same thing, but because I'm talking about sequences of random variables, I'm going to use the notation x bar subscript n here. So x bar n here is the sample mean, so 1 over n, the summation of the xi's. One thing that we learned from the previous lecture that hopefully over time will just be an automatic thing for you to write down now when you have independent normal random variables with the same mean and the same variance. The sample mean has the normal distribution with mean mu and variance sigma squared over n. So if that's not clear to you, I would go back to the calculation from the previous lecture, but really try to understand why it's true. So we're using a few properties here. We're using independence, and we're using the fact that the normal distribution has this nice property that it's closed under a linear transformation. So you remain as a normal distribution when you add independent normals. So now let's look at what this distribution looks like using my kind of limited drawing ability here. But what we can see here is if you have n equals 1, which is just one sample, that just looks like a normal which is centered at mu and has a width of sigma. Then if you look at a sample size of n, this distribution, so to be clear, so this is all I'm doing is drawing the PDF here of normal with means mu and variance sigma squared over n. You can see that as n goes from 10 to 100 to 1,000, basically that the width of that curve just gets narrower and narrower. So it's always centered at mu, but the width of that curve just the width of that distribution just gets narrower and narrower because we have that sigma squared over n. So you can see some kind of interesting behavior is going on here, that as n gets bigger, we're kind of like starting to concentrate more around the mean mu, but we're still remaining as a normal distribution. And this picture is very useful to keep in mind because it's going to be a segue into two of the results that we're going to focus on. We're going to build up towards those towards the end of as we go through the lecture. But keep these examples in mind and the end goal in mind, because we're going to build to these two key results. So what are some observations that we can make from these two curves? So we can say okay, so as I mentioned, I'm just putting in the observations that I just made into words here. The first one is that as n gets large, most of the mass is concentrated around mu. And this is a vague statement, and we're going to make this precise today. And then regardless of how large n is, it looks like a normal distribution. And in particular, as n gets large, it looks like a normal distribution. And so, I mean, again, these are just very sort of vague statements at this point. But this is going to be the segue or observations. Lead to the law of large numbers and the central limit theorem, which we'll get to. We'll certainly get to the law of large numbers by the end of this lecture, and we'll potentially get to the central limit theorem in today's lecture, but maybe in the next lecture. Okay, but we're gonna have to build up towards that because we're starting with an example with some vague statements, and we want to kind of make that statement more precise. So we're gonna to make these notions precise and to give us the two really key results in I would say in probability and statistics, which are the law of large numbers and the central limit theorem. We need to discuss this notion of convergence of random variables. So we have okay. So what we want to do by precisely defining our convergence of random variables is that we want to say that yn gets close to y, some random variable y as n gets large. What does gets close to really mean? And it turns out that there are many different notions of convergence of random variables, unlike real numbers actually. So real numbers, real or complex numbers, there's only one sort of standard notion of convergence that's really used. But for random variables, there's many. And in this course, we're going to focus on two, the convergence and probability. And the reason we do that is because that's the building block for the law of large numbers. That's the definition of convergence we use for the law of large numbers. And then the second notion is the convergence and distribution. And that's what we'll be using to show that to prove or to show the central limit theorem. So that's the notion of convergence that's used for the central limit theorem. So let's begin with convergence and probability. Okay, so the notion of convergence and probability, I'm just writing down the definition, and once again, you've hopefully seen this definition before. Um, we use like all of these definitions go back to the notion of convergence of real numbers, because there's one natural notion of convergence of real numbers, and so I'm using this notation limit to be real numbers. And so a sequence of random variables y1 through to yn converges in probability to a random variable y if for any choice of epsilon, no matter how small it is, it's bigger than 0. You can show that yn and y are very, very close, and that the probability that it's bigger than some epsilon is going to be equal to 0. So just to unpack this definition a bit, so you can see that so this is real number. So we have a sequence of real numbers. So we have a sequence of real numbers here, a1, a2 up to an, where and so on, where an is this probability that yn minus y is bigger than 0, and we say that an converges to 0 as n goes to infinity. So that's what this statement's basically saying. So, again, you've hopefully seen this before, so I won't spend too much more time on it, but we'll illustrate this with a couple of examples. So just to go back to that to the example of the distribution of normal of the distribution of x bar n. So as n gets big, what this is basically saying is that if you imagine that your like so let's illustrate this. So let's think about this example. Yn is equal to x bar n. We said that most of the mass is concentrated around mu. So what we're actually going to show is that, and we're going to show later, I'm just going to kind of explain intuitively here, is if we let y equals mu, so this is a constant, this random variable mu is a constant, and that's perfectly okay. We can actually, this is going to be the law of large numbers, but intuitively, what's basically going on if we go back to these distribution plots? If you look at mu plus epsilon and mu minus epsilon, and look at the probability that you kind of sit outside that, you can see that for n equals 1, that probability or area is quite large. But as n gets kind of bigger and bigger, so if we look at say n equals 1,000 and look at mu plus epsilon and mu minus epsilon, you can see that the area under that curve in that area is getting very, very close to 0, and that's why we're seeing some notion of convergence in probability here. But we're going to show that, or we're going to express that rigorously later. Okay, so let's look at an example where we can precisely show this here. So we're going to use another distribution which we covered in the previous lecture, which was the uniform distribution. And we're going to let yn here be the maximum. So here, this notation here, x of n, is just the maximum of x1, x2 up to xn. So imagine that you have these n random variables, and then you just take the largest value of them, and they're all distributed with the uniform 0, 1 random variable. So once again, you can see that as n changes, your maximum's going to get bigger and bigger, hopefully. So it might eventually stay at one point, but it's only going to get bigger as n gets bigger. So what does yn, which is this maximum of these n independent uniforms, converge to? So I'll let you think about that for a second. So I would, if I were you, I'd pause the video at this point. So I'm gonna just write pause to make this more explicit, and just think about this for a minute. So okay, so hopefully if you've paused and then restarted, you can hopefully see that if you set y equal to 1, so then, or you might expect that xn gets close to close to 1, because as you're drawing from this uniform 0, 1, you're expecting that maximum is going to get bigger and bigger and closer to that endpoint of 1. And so the question is, we want to prove that x of n converges in probability to 1. Okay, so at this point, I'll ask you to pause video for 5 minutes and do this exercise yourself. Okay, and this is something I'll ask you to do just to make sure that while you're watching your video lectures, you're staying engaged and hopefully not completely falling asleep. So pause the video and I'll return and go through it after you've tried it for 5 minutes. Okay, so let's hopefully you've stopped and paused for 5 minutes. So I'll return now. So we okay, so we need to show that if for any choice of epsilon bigger than 0, that the probability that x of n minus 1 is bigger than epsilon is equal to 0. That's just the definition. Okay, so now let's think about that. So what does that actually mean? So we know that x of n equals max of x1, x2 up to xn. Okay, and so now let's think about different values of epsilon. So if epsilon is bigger than or equal to 1, we have that that this is just equal to 0 trivially, because the maximum, we can see that x of n has to be between 0 and 1, because we're only distributed on the uniform 0, 1, and if you recall the uniform only has a support or a range on 0 to 1. So we're only interested in, so the only non-trivial choice of epsilon is, we're going to only focus on epsilon between 0 and 1 here. So the probability that you can, again, see that there's only really one direction here that's interesting because, if you think about this absolute value, the probability that x of n is bigger than 1 plus epsilon is 0. So you can think about this as the probability of x of n is bigger than 1 plus epsilon plus the probability that x of n is less than, 1 minus epsilon. So this is the definition of absolute value that we're using here. And so this first term is just 0 because, once again, x of n is between 0 and 1. So you can just rewrite this now as the probability that x of n is less than 1 minus epsilon. Okay. So this is where we can exploit we're looking at the probability that the maximum of x1 through to xn is less than 1 minus epsilon. So now we're going to exploit a key property of maximum. So if the maximum of n random variables or n numbers or anything like that is less than or equal to some value, what does that mean in terms of events? That means that every single one of those n random variables is less than that number. Like if I tell you that the maximum points that are scored over n basketball games is 103, that is less than 103. That means that there's less than 103 points scored in every one of those games. So we can now re-express this as the probability that okay, and so we now can break this down into these intersection events. This is something that you've hopefully seen before in 309, but just try to go through the logic in your mind if it's not completely clear. When you're talking about the maximum of n random variables being less than a particular value, that's equivalent to talking about the that all of those n random variables are less than that particular number. What can we do next? So the next thing we can do is, because we have independence here, one of the properties of independence is that we can split this intersection up into products. So this is where we've used that property of independence. Okay. So this is again just using the fact that we have because we have these n random variables that are independent. All of these events are independent, and therefore we can just, the probability of the intersection of n independent events is this the property of the product. So to be clear, I'll just use multiplication here so there's no confusion there. And so for each xi, the probability that xi is less than 1 minus epsilon, that just equals to 1 minus epsilon since xi is distributed uniform 0, 1. So if you recall, a uniform 0, 1 is the, it's a very nice, simple, continuous distribution that is flat from 0 to 1. So if you look at 1 minus epsilon, that area there is just 1 minus epsilon. Okay? And so what we then have is this calculation just becomes 1 minus epsilon times 1 minus epsilon times. And so we get this very nice expression of 1 minus epsilon to the n. So the upshot of all that is that if we're in this range of epsilon 0 to 1, which is the only range that's really interesting here, because the statement that we're interested in is trivially true for all epsilon bigger than 1, then we get this nice probability. And now, as I mentioned, this is just real numbers, 1 minus epsilon to the n, which is like those a1 up to an that I mentioned earlier. And let's recall that to show that that this thing is converging in probability, we have that we need to show that this converges to 0. And indeed, it's very simple to show that it does. You've got a number that's between 0 and 1, and you're raising that to the power of n. As n gets big, that obviously converges, that obviously equals 0. And so therefore, we've proven that xn converges in probability to 1. And I'm going to use this notation from now on. Okay, so in general, I'm going to use this notation where we use this arrow with a little p above it to say convergence in probability. And the reason we do that, and hopefully you've seen this notation before, is because there's multiple notions of convergence. And so we want to indicate that convergence here refers specifically to convergence in probability. So that's why we're going to use this notation. So now we're going to go to the first key result, which uses this notion of convergence in probability, which is the law of large numbers. And I'm going to use this acronym LLN throughout the course. So I'm just getting you used to that here. And so we're going to return to the setting of Okay, so there are various ways this result is stated, but what we're going to do is to assume that we're going back to this scenario of n independent random, or any number of independent random variables, and then we're looking at and for each random variable, they're independent, and we know that the expectation is mu and the variance is sigma squared. So this is a little bit more general than the earlier setup where we have a normal random, where we just assume that these are all normal. Okay, so the law of large numbers states that so if we let x bar n be the sample average, or if we look at 1 over n summation of xi, then we have that x bar n converges in probability to mu. So what that means is that if you look at the limit as n goes to infinity of the probability of x bar n minus mu bigger than epsilon, then that's going to go to 0. And so once again, I'm going to kind of illustrate this with the example that we started with. So if xi is normal, mean mu, and variance sigma squared, then remember that we have this nice property that the sample mean has this distribution, normal with mean mu and variance sigma squared over n. And so what we're saying is that this area under the curve, so this is for n equals 1, so you can see that this area is quite large. But if you, for example, go to like, let's draw it here. N equals 100. That width basically gets shrunk by a factor of 10, so it's going to look more like, with my limited drawing capabilities, something like this. So if you look at this area under the curve now, it's getting very, very small. And then as you make that like 1,000 or 100,000 or 1,000,000, that's going to go to 0. So we can see that so the area under the distribution goes to 0 as n goes to infinity. The important thing, though, is that the law of large numbers holds for any distribution. And this goes, like, for example, if we have these xi's Bernoulli P independent, which is like the or like the vote in the voting example, you know, we have these yes, no random variables. Then we know that E of xi equals P, and then variance of xi is just P times 1 minus P. And so what the law of large numbers says is that that x bar n converges in probability to p. And sorry about the confusing notion that we have p for convergence in probability here and p for the probability of the Bernoulli random variable. And this is kind of nice because it just says that therefore sample average gets close to population average. That's essentially what the law of large numbers says, and it's, this makes it a very and so this is a very nice useful result. Okay, so if you're getting tired now, this is probably a good time to take a break before we move on to the next topic. Okay, so just to I just want to quickly go over the proof overview. I'm not going to go through the proof. It's something you can look up in the notes. Or in the textbook. The textbook has the proof as well. So you want to show that you want to show that this limit goes to 0 for all epsilon bigger than 0. So you need a tail or concentration bound. Bound for this probability, we are not making any assumptions on the distributions of the xi's. So this is in general not a very simple thing to do. So in the previous example we saw with the uniforms and the maximums, we knew the distribution of the uniforms, so it worked out nicely that we could actually calculate this probability exactly. In general, you can't do that, but what we can actually do is to upper bound this probability. And so what you end up doing is using Chebyshev's inequality, and I'm not going to derive that. So you have what Chebyshev's inequality tells you is that that we get this variance of x bar n over epsilon squared. And so again, another calculation that's come up over and over again is what's the variance of this x bar n, which is the variance of and so when you have a variance of a constant times a random variable, you just bring that constant out and square it. And then the very important thing that goes on here that we can do is by independence, we can bring the variance into the sum. So this uses independence. And this is where we exploit the variance being some finite value. We're summing up sigma squared. And so this gives you sigma squared over n. So this is going to be less than or equal to sigma squared over n epsilon squared. And if you look at the limit of both sides, and so we get 0, and so that proves the law of large numbers. So I just wanted to go through that to make sure that we were on the same page there. And just to give you some insight as to why that's actually true and how we can, how we're able to kind of prove this by using we're able to prove the law of large numbers under very general conditions. Because we're able to come up with this concentration or probability bound Chebyshev's inequality, and if we assume the finite variance. Okay, and so the next notion of convergence that we're going to cover is the notion of convergence in distribution. So a sequence of random variables y1 through to yn and beyond converges in distribution to y if the PMF/PDF/CDF refers to the cumulative distribution function, which is a concept that includes both discrete and continuous random variables. If that converges to the PMF, PDF, or CDF of y, and this is convergence in a pointwise setting. So what I mean by that is that so here we're talking about convergence of one real function to another real function, which is this. I'm using the CDF here, but you could use the PMF or the PDF. I'm using the CDF just because it applies to both continuous and discrete random variables. We're saying that if you look at the limit as n goes to infinity of the CDF of yn evaluated at some real number y, that's going to be the same as the CDF at that value y. So this is what I mean by pointwise convergence. And once again, we're going to introduce some notation here. So the notation that we're going to use here is that yn converges in distribution is denoted by yn with an arrow going to y, and then we use the d above that once again because we have multiple notions of convergence, and we want to specifically refer to the fact that we're talking about convergence in distribution here. And so to finish this lecture, we're going to go through an example. And one that hopefully you've seen before at some point. And maybe it motivated the distribution. So or it motivated the Poisson distribution. So we're going to define so this is a comment that I kind of mentioned in the previous lecture, and we're going to make that that precise. So I mentioned that you can think about the Poisson distribution as a limit of the binomial distribution. So so remember that the intuition here is that this is a unit interval, and you're counting the events that occur over the unit interval. So for convenience, we're going to just say that we're looking at kind of a continuous time over a unit interval, so time 0 to time 1. And then you imagine dividing up these into equally spaced bins. And so there's n bins of length there are n bins of length 1 over n. And so the binomial distribution is basically just like counting whether there is an event in each of these bins and then just adding them up. And the Poisson is trying to convert that to continuous time. So we can say that as n gets large, starts to look like a continuous time interval. Okay, and so what we want to do is to show that the statement is in fact, we can actually make this statement precise using the notion of convergence in distribution by showing that yn converges in distribution to y. So what this is equivalent to showing is that because it's discrete, we're going to use the PMF here. Okay, so let's use the notation Py of y, which is the PMF of y. Because it's a Poisson random variable, this is something we covered in the previous lecture. It has this form, so this is the PMF of a Poisson lambda. And then we're going to look at the PMF of, I'll use this notation just to make it not too here we've got this is the PMF of a binomial n lambda over n. Okay, so all I've done is just plugged in the PMF for the binomial distribution here. So now it becomes purely an exercise in math to show that we need to show that So we need to show that the limit of these the PMFs, so for as n gets big, is just going to be this PMF of the Poisson. So which is equivalent to showing that I'm going to write out the factorials because that's going to be a useful thing to do. So we need to look at this limit and see if that we want to show that that thing is equal to e to the negative lambda. Okay, so we're going to ask that question and see if we can somehow take limits and end up with this expression here for the Poisson distribution. So let's look at this limit here, and we're kind of in an advantage here because we kind of know what the answer is here. So let's try to just get there. Okay, so what's nice is we already have the lambda to the y over y factorial here. And so we can bring that out of the limit because that has nothing to do with n. Okay, and so what we end up with is n factorial Okay, so we can now write this down as, we can break this down into these three terms here. And using properties of limits, we can look at these terms one at a time. And again, if this math is starting to get a little bit too much, just try to kind of take the big picture out of this. So let's look at this limit first. So it looks kind of complicated what we have here, but what we can re-express this as there's a lot of cancellation here because we have this n minus y factorial. We can rewrite this as n times n minus 1 times n minus y plus 1 because of all the calculations. And then we have this n times n y times. Okay, so because y is considered to be a finite number, n over n is just 1, n minus 1 over n as we take a limit is just 1, and we just keep getting 1 being multiplied together over and over again, and so this is just equal to 1. Okay, so we can now, we've gotten rid of that limit, we've gotten rid of that term, and so we just have Okay, so now we have limit as n goes to infinity of this 1 minus lambda over n times n here, or to the power of n, sorry. So this is something where it's a bit more challenging this time because we have this n on the inside, which seems to suggest that everything should be converging to 1, but you're actually raising it to the power of n. And so it turns out that this limit here is e to the negative lambda, and there's a couple of ways, you might remember that from looking at limits in analysis when you studied them. Another way to try to do this is to take logs of things. So if you take a log, you'll actually see that the limit you get once you take a log is negative lambda, which is why if you don't, and so if you reverse that expression, then you get e to the negative lambda. So that's a couple of ways to see why that's true. Okay, and so now we're left with this, and because we're kind of hoping, like we sort of ideally know the answer, we're just kind of expecting and hoping that this is 1. And it turns out that it is because, or that this limit is 1. Because what you have here is that y is just a given, it's a fixed number. And you're just raising 1 minus something, and that something's going to 0. Because y is fixed and it's not related to the limit, this number is just going to 1 very quickly. And when you raise 1 to the power of anything, it's just 1. So this whole thing is just 1, and you just end up with... Okay, and so what that means is therefore, yn converges in distribution to y, or we can say that binomial n lambda over n converges in distribution to Poisson lambda. Okay, and so the point of this example is just to get comfortable with working with this notion of convergence in distribution. So we're almost done for the day. I know we're a little bit over the hour now, but I'll just finish up very shortly. So the next lecture will be the CLT, which uses convergence in this notion of convergence in distribution. Okay, so today we've covered convergence in probability, the law of large numbers, and then in the next lecture we'll finish off this whole subject of convergence of random variables by discussing the central limit theorem and how we can use that. Okay, thanks very much, and I remind you again, if there's anything that's confusing or you're struggling to kind of navigate the online material in any way, just feel free to email me and to contact me. Okay, thanks very much. Have a good day.